Hello viewers, welcome to the lecture series of food technology. In today's lecture deals on the topic entitled spectrophotometer. The present episode consists of following 5 sections. They are introduction, basic principle and theory, instrumentation, applications with respect to food analysis and conclusion. Let us see one by one. Introduction. The spectrophotometer has proven to be the most versatile, reliable and widely used of all laboratory instruments in food analysis laboratories. The majority of clinical chemistry procedures have been developed to produce colored end product which can be detected and measured by some sort of photometer. Spectrophotometry is the quantitative measurement of how much a chemical substance absorbs light by passing a beam of light through the sample using a spectrophotometer. The concept of spectrophotometry is the beam of light that is radiated towards the sample is made up of a stream of photons. When photons encounter molecules in the sample, the molecules may absorb some of them, reducing the number of photons in the beam of light and decreasing the intensity of detected signal. From the absorbance, the concentration of sample solution can be determined from the Beer-Lambert's law, which states that there is a linear relationship between the absorbance and concentration of sample. According to the Beer-Lambert's law, absorbance is the product of extinction coefficient, the length that light passes through the sample, and the concentration of solute. There are two kinds of spectrophotometers, single beam and a double beam spectrophotometer. A double beam spectrophotometer compares the light intensity between two light paths, one path containing a reference sample and the other test sample. A single beam spectrophotometer measures the relative light intensity of the beam before and after a test sample is inserted. A double beam machine makes a comparison reading easier and more stable, but a single beam machine can have measures a wider range of light frequencies, have simple optical systems and more compact. Spectrophotometric instruments measures the spectral reflectance or transmittance of visible light wavelengths 400 nanometer to 700 nanometer. Over the last decades, spectrophotometers have been utilized in the food industries for color standardization and quality control inspection of ingredients prior to use, particularly in jams, jellies, preservatives and beverages. Basic principle and theory. Spectrophotometric law conducts the qualitative and quantitative analysis of material by measuring the absorbance when the measured material in specific wavelengths. The frequently used wavelength range ultraviolet region of 200 to 400 nanometer, visible region of 400 to 760 nanometer, infrared region of 2.5 to 25 micrometer. On the basis of the different spectral region, the instruments are classified as follows: ultraviolet spectrophotometer, UV visible spectrophotometer, infrared spectrophotometer and atomic absorption spectrophotometer. In order to ensure the measurement with high accuracy and precision, all instruments should get regular correction and verification in accordance with the National Metrological Verification Regulations. One instrument cannot be used to measure absorbance at all wavelengths because a given energy source and energy detector is suitable for use over only a limited range of wavelengths. Absorption spectroscopic method of analysis are based upon the fact that compounds absorb light radiations of a specific wavelength. In the spectrophotometric analysis, the amount of light radiation absorbed by the sample is measured. The light absorption is directly related to the concentration of colored compound in the sample. The wavelength lambda of maximum absorption is known for different compounds. For example, the colored compound formed for analysis of phosphate molybdenum blue has a maximum light absorption at 640 nanometer. The Beer-Lambert's law. The absorbance and transmission of light which passing through a sample can be calculated by measuring light intensity. The Beer-Lambert's law is given by the following equations. Light absorbance A is equal to log I naught divided by I, that is equal to epsilon BC. Light transmission T is equal to I divided by I naught, that is equal to 10 to the power of minus epsilon Bc. The following terms are defined. The light intensity entering through the sample is I naught. Light intensity retained in the sample is I. The concentration of analyte in sample C. The length of the light path in glass sample cuvette is B. Epsilon is the constant called molar extinction coefficient. True linearity between absorbance and concentration according to Beer-Lambert's law requires the use of monochromatic light. In addition, a narrow band of light ensures a greater selectivity since substances with absorption peak in other close by wavelengths are less likely to interfere. Instrumentation. All spectrophotometer instruments are designed to measure absorption of radiant energy have the basic components as follows. A stable source of radiant energy or light source. A wavelength selector to isolate a desired wavelength from a source, also called filter or monochromator. Transparent container called cuvette for the sample and the blank. Radiation detector, that is phototube to convert the received radiant energy to a measurable signal, and the readout device that displays the signal from the detector. The energy source is to provide a stable source of light radiation, whereas the wavelength selector permits the separation of radiation of the desired wavelength from other radiation. Light radiation passes through a glass container with sample. The detector measures the energy after it has passed through the sample. The readout device calculates the amount of light absorbed by the sample and displays the signal from the detector as absorbance or transmission. Both filters and monochromators are used to restrict the radiation wavelength. Photometers make use of filters which function by absorbing larger portion of the spectrum while transmitting relatively limited wavelength region. Monochromators that permits the continuous variations and selection of wavelength. The effective bandwidth of monochromator about 1 to 5 nanometer is satisfactory for most applications. Cuvettes, also called as cells, are provided in pairs that have been carefully matched to make possible the transmission through the solvent and the sample. The cuvettes must be fabricated from material that is transparent to radiation in the spectral region of interest. The commonly used material for different wavelength regions are quartz or fused silica UV to IR, silicate glass above 350 nanometer to IR, plastic visible region, polished sodium chloride or silver chloride, wavelength longer than 2 micrometer. Accurate spectrophotometric analysis requires the use of good quality matched cells. These should be regularly checked against one another to detect the differences that can arise from scratches. The most common cell path for UV visible region is 1 centimeter. Care must be taken to duplicate the position of such cells with respect to the light path. Otherwise, variations in path length and the reflection losses will cause errors. General measurements procedures. As explained above, the Beer-Lambert's law forms the basis of the measurements procedure. The amount of light radiation absorbed by the compound is directly related to the concentration of the compound. The general measurement procedure consists of 5 steps. Prepare sample to make colored compound, make series of standard solutions of known concentrations and treat them in the same manner as the sample for making colored compounds. Set spectrophotometer to lambda of maximum light absorption. Measure light absorbance of standard. Plot standard curve, absorbance versus concentration. Once the standard plot is made, it is simple to find the concentration of an unknown sample. Measures the absorption of unknown and form the standard plot. Read the related concentration. Let us see the application of spectrophotometer in food industry. First one, identifying food dyes with spectrophotometers. The term spectrophotometric analyzer of food is used for various spectrophotometric sensors, devices, instruments, probes and testers dedicated to measuring physical and chemical parameters. Characterizing ingredients in food products and beverages. Non-infrared spectrophotometry is of particular usefulness for food analysis because the spectra of organic samples comprise broad bands arising from overlapping absorption peaks corresponding to CH, OH and NH chemical bonds. The main advantage of NIR spectrophotometry in routine food analysis is simplicity and speed. Usually, no sample preparation is necessary and the time of analysis is not greater than 1 minute. Another advantage of NIR spectrophotometry is that it allows several constituents to be identified concurrently. But the disadvantage of this technique is relatively weak absorption due to high moisture in food products and ingredients. There are several reasons for using spectrophotometric analyzer of food in food manufacturing industries as follows: checking the quality of food, monitoring of the food product process, providing data necessary for production control, specification of food products necessary for their labeling, precise classification of food products enabling their better pricing. There are more or less evident economic benefits behind each of them. As I mentioned earlier, in spectrophotometer, the reflected light from the sample is then split to its various components within visible spectrum. The resulting data can be analyzed to give a quantifiable measures of the sample's color. This can be especially important in food industry because food have specific dyes and therefore any deviation can cause severe problem on food quality. The manufacturer is required to strictly adhere to the product label with regards to the ingredients including food dyes that make up the recipe for each food product. Thus, food producers tend to be very careful when analyzing food colors, and there are 3 primary methods for doing so. Before food production, food producers tend to collect resource and ingredients from many places before they produce the actual end product. These ingredients and raw materials can be analyzed using spectrophotometer to ensure that no non-standard ingredients reach the production line, and this cut down on waste and save times by making sure that only approved ingredients are used for the production. During production, the food manufacturing process can sometimes involve many steps, and it is possible that food coloring could become mixed or diluted at any stage of this process. Because of this, food producers often scan small test batches of products during the production process. This is done to ensure the quality of the end product and can identify any production line levels problem before they cause major issues down the line. The manufacturer can also look into checking the color of the product as it is being produced. Color information can also be obtained in real time and can report to process control indicating whether the product color is within prescribed tolerance. After food production, there are many factors that can cause food dyes to change color. If they are exposed to either oxygen or light for too long or accidentally mixed with other dyes, even small deviations in dye color can cause big changes in the color of the end products. Because of this, food manufacturers generally test a number of product samples before the finished product is shipped to retailers or distributors. Regardless of the color being used in food, any federally approved dye will have a known quantifiable values. Because of this, food manufacturers are usually able to quickly find and identify color deviations before they can become a problem for retailers or consumers. Example: spectrophotometric analysis of wine. Wine, like many elite types of alcohol, is judged very specifically on the basis of taste. Wine enthusiasts begin evaluating quality of wine forms its color. Before even shipping it, however, the flavor for the most wine begins in the vineyard with the harvesting of certain grapes. The grapes used will set the tone for the type of wine, and the specific process used for pressing and fermentation will determine the final taste. A laboratory for analysis is a basic essential in most wineries today to allow wine to be tested and analyzed for taste and quality. Spectrophotometers can be used throughout the process to perform a more specific enzymatic analysis. UV spectrophotometry is favored because it is a non-destructive way to test liquids such as wine without disturbing it in any way. Although the spectrophotometric analysis is optional, it is important for many wineries to record the properties of their wines for their own purposes. Some of the factors that are evaluated are the hue and color intensity of the wine. The International Commission on Illumination, that is CIE scale, is standard used internationally to relay values of color in relation to lightness in combination with values of red, green, blue and yellow. Factors such as color and intensity can provide information about the quality of the wine. Phenols are chemical compounds found in alcohol that contribute to the body and structure of the wine. As the wine ages, these compounds will oxidate. The physical and chemical changes due to oxidation then the wine goes through over time can affect its quality and therefore need to be evaluated. In regard to color, a white wine may begin to look more gold than green as it ages and red wine appears more brown. However, wine analysis does not have to wait for the lab. It can actually begin on the vine. NIR spectroscopy can be used in this instance to determine color quality and phenols just through the skin of grapes in the vineyard. NIR spectrophotometer is able to determine ethanol, glucose, fructose, malic acid, volatile acid, total acid and pH in finished wine or under fermentation. The next application, estimation of protein by spectrophotometric analysis. Since protein absorbs light at specific wavelength, a spectrophotometer can be used to directly measure the concentration of purified protein in solution. It is important to note that direct UV measurement at 280 nanometer yields highly reproducible measurements since no reagents are added to the protein solution and the protein of interest was not modified or inactivated during the process. It also produces quick results since the sample does not need to be incubated in order to complete the process. The chemical composition of the protein, that is the number and the type of amino acid present, will affect its absorption since a sample protein's absorption at 280 nanometer will depend on the amount of amino acids, tyrosine and tryptophan. It is very much possible that protein of similar molecular weight will have different absorbance values due to their different tyrosine and tryptophan content. In addition, the structure of your protein of interest may also affect the UV absorbance of aromatic side chains. As such, the temperature, pH, ionic strength and presence of detergents can affect the ability of aromatic residues to absorb light at 280 nanometer and change the value of protein extinction coefficient. Procedure: warm up the UV lamp for 15 minutes, adjust wavelength to 280 nanometer, calibrate to 0 absorbance with buffer solution, measures the absorbance of the protein solution, adjust wavelength to 260 nanometer, measure absorbance of the protein solution. Also, ASD's portable bench top and online visible NIR instrumentation provides the flexibility to measure where and when it is most advantageous to you. Gone are the days of collecting samples, sending them to a laboratory and waiting for the results. ASD's visible NIR measurements technology offers the cost-effective solutions you needed to easily analyze product in the field, on the receiving dock, in the warehouse or manufacturing facilities, even though glass and most clear plastic bags and bottles. Monitor in process and finished products to ensure quality and consistency. minimize the risk of product and material waste. Visible NIR spectroscopy has been successfully used in the production of cheese, eggs, milk, butter, beer, wine, fruit juices, baked goods, cereals, jams and jellies, nutritional supplements, fish and more. Some of the more common applications include fat level, protein content, moisture content, particle size, sugar content, Brix and acidity levels, blended analysis. Scientists are also utilizing visible NIR spectroscopy to develop specific aspects of ingredients to enhance the nutritional quality of food and beverages. The quantitative determination of caffeine in beverages and soft drinks using UV spectroscopy. Caffeine is a naturally occurring alkaloid which is found in the leaves, seeds or fruits of over 63 plant species worldwide. The most common sources of caffeine are coffee, cocoa beans, kola nuts and tea leaves. The worldwide consumption of products derived from these natural materials means that caffeine is one of the most popular and commonly consumed drugs in the world. Caffeines gain more popularity because of the biological significance and proved as a mild central nervous system stimulant. It is generally agreed that there is a little risk of harm when a person consumes less than 300 mg of caffeine a day. However, at times of anxiety or stress or during pregnancy recommends the consumption of less than 200 mg a day. While there are no regulatory requirement to control the label of food products with their caffeine content. Numerous studies have been carried out to determine the typical caffeine content of commonly consumed beverages. A wide variety of methods have been employed, with high pressure liquid chromatography being the method of choice in many analytical studies, as it commonly is subjected to fewer interferences than alternative methods. HPLC is an expensive and laborious technique that is not typically found in the scientific teaching labs of schools and colleges. Therefore, HPLC method of application note will be investigated an alternative analytical method that use UV spectroscopy to analyze and quantify the caffeine content of some common beverages and soda drinks. Caffeine can be extracted from aqueous solutions with chlorinated solvents such as dichloromethane and chloroform, a technique commonly employed commercially to decaffeinated coffee and tea. After the caffeine is extracted, it can be analyzed directly by measuring the absorbance of the solvent solution at 260 nanometer. Let us see the method and procedure for the determination of caffeine. Standard caffeine, dichloromethane, purified water are required reagents in this technique. In the first step, standard preparation. 1000 ppm stock standard of caffeine was prepared by dissolving 198.2 mg of caffeine in 200 ml purified water. Working standard were prepared by pipetting 25, 12.5, 10, 7.5, 5 and 2.5 ml liquids of stock standard solution into separate 50 ml of volumetric flask, diluting to volume with purified water. Sample preparation. Take 200 ml aliquot of boiling purified water to each of 250 ml beaker containing 2 gram of instant coffee or tea. The coffee and tea preparations were stirred for 30 seconds using magnetic stirrer at 500 rpm and allowed to cool to room temperature. The soft drink samples were used as supplied by the manufacturer. Caffeine extraction procedure. A 50 ml aliquot was taken from each working standard or sample solution. This aliquot was placed into separating funnel and 25 ml dichloromethane was added. The caffeine was extracted by inverting the funnel at least 3 times, venting the funnel after each inversion. Dichloromethane layer was removed to a clean flask and the extraction procedure was repeated twice more and solvent layers combined. Sample measurement. Aliquots of extracted standard were placed into quartz cuvette and analyzed using spectrophotometer. The concentration mode was then used to quantify the caffeine concentration of the sample solution with measurements performed against a dichloromethane blank. Conclusion: spectrophotometer is an instrumental technique which is used to measure the reflectance or transmittance light of object across the full spectrum of visible light wavelength 400 nanometer to 700 nanometer. The spectrophotometer is working on the basis of Beer-Lambert's law. It offers greater specificity, making them the instrument of choice for food product color formulation. Specification of standards and tolerance, interplant color communication and color quality control in processing operations. Thank you.